Hey everybody, this next video lesson is going to discuss the behavior of ideal gases, and we're also going to take a chance to compare ideal gas versus the behavior of real gases. The gas laws tell us what happens mathematically, but not why it happens. And in order to understand why gas laws work, you need to take a look at the gas particles down on the microscopic level. In science, what always comes before why, but the why in AP chemistry is just as important. And so we're going to talk about the kinetic molecular theory of gases, or basically a couple of statements to describe the behavior of gases, specifically the ideal gas. But like I mentioned, we're going to deviate a little bit and talk about how real gases compare to ideal gas. You can find this information in the reading on page 403 in your textbook. The first statement we'll talk about is this first one that you see on the page in green. The particles are always in constant motion. This is true of ideal gases and real gases. The collisions of the particles with the wall cause pressure to be exerted on the container that the gas is contained in. And so the warmer the temperature, the faster the particles are moving, and the more collisions. Basically, if you have more collisions, you have higher pressure. As we know from Gay-Lussac's law, increased temperature, you increase the pressure of the gas, but that is due to increased particle collisions. That's the why, not just the what. So as you can see, these gas particles are at a lower temperature, and they're colliding, and the vectors you see are very small compared to the ones that you see on the right. If the gas particles are moving slowly, then their collisions with the container result in a little bit of pressure. But if the gas particles are moving fast, you can see the vectors are much larger, which means that they are moving faster, and hot gases exhibit more collisions and thus have a higher pressure. This next statement, like the first one, is true of the ideal gas and real gases. The particles of a gas are so small compared to the actual distance between the particles that the volume of the individual particles is assumed to be zero. In other words, the actual volume of the gas is negligible compared to the overall volume of the gas itself, if you factor in all the empty space between the gas particles. As you see on the left, we've got solid ice, and the particles are packed very tightly together. So the volume of the solid is the volume of the particles. But as far as gases are concerned, the particles are so far spread apart and the particles themselves are so small that the actual volume of the actual particles does not contribute to the volume of the overall gas. And so all of the empty space is what makes up the volume of the gas. And as we learned in a previous video lesson, 1 mole of any gas is always equal to 22.4 liters, regardless of the identity of the gas. Now the gases may be heavier or lighter than other particles, but the volume has nothing to do with the mass. If you take the mass and divide by the volume, you get density, but the volume itself is not affected by the mass of the particles. So if you have helium gas inside, 1 mole of it would occupy 22.4 liters. Or if you had a heavy gas like sulfur hexafluoride, that is a very heavy gas, but it also occupies the same amount of volume if you have 1 mole of gas particles in the container. Now these next two are different when it comes to describing the ideal gas versus the actual or real gas. Number 3 and number 4 are things that we assume to be true for the ideal gas, but are not true for real gases. Statement 3 says that the particles are assumed to neither attract nor repel one another. Now in real situations, the particles definitely do attract and do repel one another. But in the ideal gas, we assume that this attraction and repulsion is not there. Anything with mass will have a slight attraction. Even if it's a nonpolar molecule, nonpolar molecules will eventually attract one another if you cool the temperature down enough. The evidence of this is that these gases will turn to liquid if they're cooled low enough. Now you have to get pretty cold, like liquid nitrogen needs to get to negative 200 degrees Celsius in order to turn from gas into liquid. But the fact that it does turn to liquid is evidence that these particles indeed do attract one another and form liquid at low temperatures. But we're going to assume that the particles are moving, and they're moving so fast that they neither attract or repel one another when they collide or come close. Speaking of collisions, let's talk about statement number 4. It says all the collisions are elastic and the energy is conserved, which means that when the particles bounce into one another, they don't transfer energy from one particle to the next or even from the particle to the container. Oftentimes, the pressure is contributed to the particles striking the inside of the container that the gas is contained in. And if the particles are striking very quickly or more frequently, then the pressure is increased. Those collisions result in a net loss of energy, but we're going to assume that the energy change in these collisions is not lost and all of the energy is conserved. We call it an elastic collision. Finally, statement number 5, the average kinetic energy of a gas is proportional to the Kelvin temperature of gas. And this is once again true of ideal gas and real gases. These 5 statements all help explain the behavior of the ideal gas. Now let's discuss when the real gases deviate or stop behaving like the ideal gas. Now in normal atmospheric conditions, real gases behave almost very similar to the ideal gas. But when you start messing with the conditions of the gas, specifically the pressure and the temperature, then the real gases stop behaving like the ideal gas. This information is outlined on page 409 of your textbook. In a situation where you're changing pressure or temperature, we need to then account for deviations from the ideal gas behavior, specifically when you increase the pressure or you decrease the temperature. Because under these conditions, when you increase the pressure, you are concentrating the gas particles into a smaller space. Typically, in order to increase the pressure, you decrease the volume. If the particles are colliding more often with the container that it's contained in, then the particles are also more likely to interact with each other. And when they interact with each other, they're more likely to attract and repel one another. And as we talked about before in the kinetic molecular theory, we assume they don't attract or repel, but now we're talking about real gases. And real gases do attract. And if you pack them in tighter or increase the pressure, increase the collisions, then they're more likely to deviate from ideal gas. Because when they collide more often, their attractive forces become a more important factor. The same is true when the temperature is low. Once again, we are slowing down the temperature, which means that the particles aren't moving as fast. The average kinetic energy decreases. And when they're moving more slowly, then those attractive forces, which are always present, but when they're moving slowly, then those attractive forces begin to factor in. They're attracted to one another and they slow down and they become liquids from gas. They condense. Only under low temperatures is this true. They're moving slow enough, the attractive forces can take hold and they form little droplets of liquid inside the container. The gas is no longer gas at low temperatures because, once again, the attractive forces are an important factor. So under high pressure and low temperature, real gases begin to deviate from the ideal gas behavior. Here's a graph that shows the effects that pressure have on different real gases. As you can see, we have nitrogen gas, methane, hydrogen gas, and carbon dioxide. Now the ideal gas you see is this dotted line, and it stays steady at the 1.0. Now what is that number? Well, if you take the pressure as standard, which is 1 atmosphere, and the temperature as standard, which is 273, and a standard volume of 22.4 liters, and the ideal gas constant, and you multiply those two and divide by those two, then you get 1 mole of gas, which is true of the ideal gas. But now we're going to start changing the pressure and increasing the pressure. Now there's not just a little bit of pressure increase. You see that the pressure jumps 200 atmospheres. So we're talking about 200 times atmospheric pressure here. You can see, no matter what the pressure is, when you effectively change the pressure, the ideal gas behaves like there's only 1 mole of gas in the container. But that's not true of real gases. Let's first start looking really close at pressures close to 0. Do you see right here in this little picture inset that says between 0 atmospheres and up to 1 atmosphere pressure, all the gases behave pretty much like the ideal gas. They stay close to that 1.0 line. You see a little bit of deviation right at 1.0, but it's so small that you consider them to be all the same. But now that we've moved from 1 atmosphere to 2 or double the pressure of the gas, which is about the same pressure as inside a bike tire or a car tire at about 35 psi, it's about 2 atmospheres of pressure, you can see the gases start to deviate significantly. You can see initially that as pressure begins to increase, many of these gases start to behave like there's less moles of gas inside the container. And that is due to the increase in attractive forces between the particles. The particles themselves are attracting one another more strongly, and the gas itself behaves like there's less gas inside the container, even though the actual amount of gas stays constant throughout this process. Eventually, you reach a pressure high enough where the particles are colliding so often where they stop behaving like less moles of gas and begin increasing and going up this line, you're basically forcing the particles to get so close to one another that they stop attracting each other and begin repelling one another. And that repulsion then effectively makes the gas behave like there are more moles of gas in the container than less. The initial drop is due to the increased pressure and the attractive forces making the gas behave like there's less moles of gas in the container than there really is. Usually someone pipes up from the peanut gallery and asks me, what about hydrogen? Why doesn't hydrogen take an initial drop? Why does it just go up right away? And truthfully, I can't explain it scientifically, so you're just going to have to sit with that one on your own. As you can see in this picture and the caption, it says that the actual gas, the real gas, the actual observed pressure is often lower than the pressure exhibited by the ideal gas, because these gas particles attract one another, and so without the attraction, the pressure due to the colliding particles with the container in the ideal gas is much larger. You can tell by the thickness of this vector. But because this particle is actually attracted to the other particles around it, it's going to strike the container with less force, and with less force means less pressure. And so real gases exhibit a lower pressure than you would expect with an ideal gas due to the attractive forces. And this attraction becomes more obvious when you pressurize the gas more and more. If you were able to squeeze this gas into a smaller container, then these attractive forces would be larger and the pressure would be lower and lower and lower. This next graph shows one gas over a various number of temperatures. So instead of different gases here in the different lines, these are all nitrogen gas, but this nitrogen gas is at different temperatures. Now again, we're increasing the pressure, but this time by 300 atmospheres. As we move down, every data point is increased by 300 atmospheres. But once again, we're taking a look at how similar this nitrogen gas behaves to the ideal gas. The ideal gas, regardless of the increase in temperature or the increase in pressure, will always behave as though there's 1 mole of gas inside the container. But a real gas like nitrogen will not. Now in this graph, we're changing 2 variables at a time, and that's difficult to understand and interpret. So let's just hold constant at 600 atmospheres of pressure and take a look at these 3 different colored lines of nitrogen. You'll see that the one that deviates the most from the ideal gas is the coldest temperature gas. At 200 Kelvin and 600 atmospheres, this gas is behaving like there's 2 moles of gas inside the container rather than 1 mole of gas. The particles are moving slowly and it's under high pressure, and because of that, the particles are not behaving like the ideal gas. But as you increase the temperature, you actually see that it gets closer to the ideal line being flat at 1 mole of gas. In fact, it almost cuts in half. The temperature increases and it lessens the effects of pressure that the pressure has on the gas. And you increase the temperature even more, you can see at 1000 Kelvin, it becomes closer and closer to the ideal gas. So in other words, the conclusion you can make from this graph is that even though at high pressures, you can offset the pressure by increasing the temperature of the gas to make a gas behave more like the ideal gas. Hot gases behave like the ideal gas, regardless of the pressure. I said this on the last slide, but here it is in writing. For real gases, a high temperature gas can lessen the effect of the attractive forces that pressure puts on the gases. So under high pressure, the attractive forces increase. But if you increase the temperature, then those attractive forces are less likely to make the gas behave differently. At normal atmospheric conditions, the temperature is warm enough and the pressure is low enough where real gases behave very similar to the ideal gas. But as soon as you start lowering the temperature colder than atmospheric temperatures or increasing the pressure higher than atmospheric pressure, then the real gas starts to behave not like the ideal gas. So in summary, real gases behave like the ideal gas at high temperatures and low pressures. Here's a screenshot from one of the questions at the end of the chapter problems in our book. It's not one that we necessarily assigned for our problem set, but this is definitely a question that you'd be likely to experience in an upcoming quiz or test. So let's take a look at this problem. It says Jupiter has a surface temperature of 140 Kelvin. Remember, 0 degrees Celsius is 273 Kelvin, so this is colder than 0 Celsius. It says it has a mass of 318 times that of Earth, but Mercury, the planet, has a surface temperature of 600 Kelvin, and a mass of 0.05 times that of Earth, which planet is the atmosphere more likely to obey the ideal gas law? Now, initially, you might be wondering what the mass has anything to do with this, but the mass affects the pressure. If something has a high mass, then the atmosphere is going to be much more dense. And that means if it's more dense, then it's going to have increased pressure. And so Jupiter has a low temperature and a high pressure, whereas Mercury has a high temperature and a low pressure. And as we talked about, anything that has a high temperature and a low pressure is going to behave more like the ideal gas. So in this case, Mercury is the one that's going to have gases behave more like the ideal gas. Be able to explain using pressure and temperature. Not just saying Mercury, but be able to explain why. Anyway, that takes care of this video lesson. Thanks for watching.